everyone, welcome back to the YouTube channel. I hope all of you are doing great, and I know today is the first day of A-levels, so all the best for your A-levels until the last paper. Well, you can do it, just relax and calm your nerves and you'll be fine. So today we'll be talking about simple harmonic motion. So I have mentioned about phase constant in one of the simple harmonic motion videos episode, one of the episodes. But today I learned something new, something more detailed, which is phase constant as well as phase of motion. So just a disclaimer, this is not part of A-levels. This is just for your further understanding if you wish to know. Okay, so let's get started. So if you see, I have a picture here. I think you're familiar with this picture. I've shown this picture before. Is you derive the function of x using the circular motion rate. Okay, now, so let's draw a cos graph first. We have a cos graph here. Okay, why cos graph, why not sine? You can draw sine also, no problem. Here given is cos, so I'll just show you in a cos function graph. Okay, let me move this a bit. Oops. Okay, I just realized. Okay, never mind. I move that one. Okay. So we are looking at a function of x against time. So we have a function of x, right? Function of x as a cos omega t plus phi. So you are familiar with this one, right? So now what we're going to do is we're going to start with doing from the beginning by drawing the basic cos graph. Okay, I know my graph doesn't look that nice, but you get the idea, right? Okay, it's even better. So this graph is actually xt equals to a cos omega t. That's it. Or in other words, to put it simply, is basically y equals to cos x. If this is y against x graph, then it's just y equals to cos x graph. Right. Okay. Now, let's go and see what is the meaning of phase constant. So I have said before, in my previous video, the phase constant is basically the angle that you shift, whether is it to the right or whether is it to the left. But I did not mention that phase constant is also known as the initial phase angle. That is something that I learned today. And why is it called as the initial phase angle? Okay, so now let's say, okay, I'm going to draw another cosine graph. Okay, I'm going to move this graph. Okay, I'm going to move this graph, let's say, to somewhere here. Okay, so if you realize I have shifted the graph to the left, that means now the pink color graph will have an equation of x with respect to time equals to a cos omega t plus pi over 2. Remember, if it's plus pi over 2, that means you shift your graph to the left. If it's minus pi over 2, you shift your graph to the right. Okay, so now that I've shifted my graph to the left, I have shifted by pi over 2. So now my particle is going to start at this point, which is 0, 0, with a displacement of 0. After it starts at 0, it's eventually going to move down. Right? Okay. So this is what we call as initial phase angle, because this is now where I start. So initially, this is just our graph. I just draw the basic cos graph. Now I've shifted the graph. So I shifted the graph by pi over 2. And after I have shifted, this is my initial phase angle. How much I have shifted to the left. So now this is my starting point. So to put it simply, phase constant is where does it begin, and phase of motion is where is the point now. Okay, let me write. where is the point of particle now, and phase constant is, oh my god, my handwriting, where does it start? So now the particle is starting at this point after being shifted to the left by pi over 2. So this is where it starts. Okay, so let me draw. Oops, I wrongly erased the line. Let me erase this. Okay, so this one we have shifted here by pi over 2. So this is pi over 2. This is your phase constant. So let me summarize again a little bit on the phase constant. Phase constant is how much you shift, either to the left or to the right. And after you have shifted it, so you shifted to the left, that means it's plus pi over 2. And now my particle is going to start at the displacement of 0, x equals to 0. And since it's starting at x equals to 0, that is why, in other words, we call this phase constant as the initial phase angle. Initially, it has moved to the left by pi over 2. Okay, that's it. That's about phase constant. The extra thing you learned today is that it is also known as the initial phase angle. Okay, now, what is phase of motion? So let's say we are looking at my pink graph now, right? Okay, let me erase this. We are looking at my pink graph now. Okay, so let me just highlight the pink graph so you can see. Okay, let's look at the positive side for now. Okay, for simplicity, let's look at the positive side. It works for negative side also, but for time being, let's look at the positive side. Okay, now, phase of motion, like just now I said, we want to know where is the particle now. So let's say my particle is now from here, it has now moved here. So it has moved for a certain angle. There's a particular angle it has moved through, and this we call as omega t. That is the angle it has moved through. If you have your time, you have your omega, angular frequency, which is constant throughout simple harmonic motion, and then you add by the pi over 2 the angle that you have shifted initially, you will get exactly the point where your particle is now. Understand? So let me go from the beginning. First, we started with the basic equation, a cos omega t. Okay, then we shift it to the left by pi over 2, and this is the point where we start. So we call it the initial phase angle. Now I want to move my particle. My particle starts moving down, let's say, and I found a point. My particle stops, and I want to know at this particular time, where is my particle now? Let's say at time equals to 3, where is my particle now? For you to find that, you need to measure what angle is this, and you can measure that by taking omega t. Omega multiplied by t, the given time. Make sure you take omega t, which is the angle that the particle has moved through at that particular time. For example, here is t equals to 3. So at time equals to 3, this particular particle has moved through a certain angle of omega t. Omega is usually given, it's a constant. Time, t, I have said, whatever time you pick. At this point, I picked 3. Then, make sure you add by pi over 2. That is why your equation will look like this. Pi over 2 plus by omega t. This omega t is the angle that the particle has moved through. So you add both, you will know exactly where the particle is now. If you're going to just put it as a cos omega t, that means you're just going to sub in this angle inside here. You will not get the right answer, because this shows that you have not shifted the graph at all, which is ideally wrong, because we have shifted the graph. You have shifted the graph to the left hand side by pi over 2. You take the pi over 2, now add together with this to know exactly where your graph is at the point of, for example here, t equals to 3 seconds, for instance. Okay, so phase constant is where does it start. Okay, we have moved it by pi over 2, so that is exactly where it starts. And that is the initial phase angle. Phase of motion is where the particle is specifically now. For instance, I have picked this point just now. And you measure this angle, which can be measured using omega t. T your time, omega is angular frequency. Then add by pi over 2 because we have shifted by pi over 2. So we must take that into consideration. Shifted by pi over 2. You add them, you will get your phase of motion. Okay, so another way to look at this is using circular motion. Okay, since they gave here cos graph, okay, I'm just going to draw a cosine graph here. Okay, I'm going to draw two graphs, okay, because I need to use one later to move. Okay, so now they are telling me the initial position of the particle at t equals to 0 is at here. That means my particle is going to start at this point here. So I'm going to shift my graph until it hits that point. Okay. So since the graph is supposed to be here, right, this is where it starts together. Because I'm trying to draw an equal graph. Then move. That. It has stopped there. So my graph has been shifted to the left by this angle. This, which is what is being shown here. From the original point, it has been moved to phi naught, angle phi naught. I know it's not accurate here, but yeah, you get the idea, right? Yeah. It has moved through the angle of phi naught, which is what you can see in the circular motion diagram. Okay. After that, they ask, okay, now what will my angle be at this point? So if we were to bring this all the way here, it's here, this point here. So what we need to do now is we need to find this angle, the angle that this particle has moved, because the particle from here has go all the way here to all the way up here. Okay, I think I better draw my graph properly. Okay, better. To all the way up here, the green color highlighter, all the way up here. So we need to find what is the angle it has moved through. Looking back at the circular motion diagram, we'll understand better. This is the angle that it has moved through, and it is calculated by using the formula of omega t. Then you add both of these, omega t plus phi naught, you will get your phase of motion. Understand? Which is the total angle. So this is omega t. This one, it has moved just now for phi naught, right? So you add both to know your phase of motion. That means where is this particle exactly now? Don't forget to add by this, because we have shifted the graph by this phase constant. Then from there, we are calculating the angle. Okay, so if you look at this graph, not the graph, the circular motion diagram, initially it was here, right? Then it has moved through an angle of phi naught. Then from the phi naught, from this line, okay, from this line, it has moved to another angle here. So it has swept through another angle, and this angle can be calculated using omega t. The t is what is the time at this. For example, time equals to 3, you sub in t. Angular frequency, like I have said, it is always constant. Then, to know your phase of motion, you take this phi naught, add by omega t. So that's about it for today's video. Two new things we learned: phase constant and phase motion. Phase constant is another way of saying it is the initial phase angle, because when I move through, for example, because I'm not sure what angle is this, you can calculate this by taking the time. Okay, you take the time, times divide by your period times 360. You will know this is to get degrees lah. If it's radians 2 pi, you'll get the exact angle that it has moved through to the left. So it has moved through this angle, and that is now your starting point. That is why we tell that is your initial phase angle. Then after that, I want to know where is this particle now exactly. For example, at this point we pick, and we see it has moved through a certain angle. From here, it has gone through all the way here. It may be a bit difficult to see through this graph to see that it has moved through an angle, but if you look at this, you can see that from here it has moved through an angle, and that angle is omega t. Then to know exactly where it is now, you take phase constant plus omega t. Don't forget to plus your omega t and your phase constant together. Why we need to plus phase constant? Because we have shifted the graph. Because if we do not take this into consideration, we're just going to take this, it's going to be hanging there. It's wrong because we have already shifted the graph. So we must take into the consideration that we have shifted the graph. Yes. So from there, from here, take this plus omega t to know exactly where it is at this point now. Okay, so that's all from me. Thank you. Wish you luck and bye bye. I'll see you in the next one.